Hello everyone. We're gonna continue with chapter 5 and are now at section 5.4 looking at normal random variables. Most of you have seen this bell curve at some point in your career as a student, even maybe in middle school or high school, I'm sure. Anyway, so let's start with what the definition of a normal random variable is. And all of these continuous random variables, or for that matter, discrete random variables, we define them via their probability density function or their probability mass function, respectively. So we say a random variable x is normal with parameters mu and sigma squared if x has a PDF, the probability density function given by this. Okay? And you can also write x is normal, mean mu, variance sigma squared. That's a shorthand notation, though it's not used in this book. Okay, and if you like, you could include this sigma under the square root and write a sigma square. Therefore, everything that appears is with a square. I prefer doing that, but you can leave it outside just as a sigma if you like. Okay, the graph of this function looks like this. This is the best I've drawn on over here. It's supposed to be symmetric about this line x equals mu, and you have x equals mu plus sigma, mu plus 2 sigma, mu plus 3 sigma, mu minus 2 sigma, mu minus 3 sigma. And what you have is the area outside of this interval, mu minus 3 sigma and mu plus 3 sigma. This area is very small. So this is the density, right? So you remember, the probability x is in any interval is given by the integral over b of that density function. So in fact, the probability that x is less than mu minus 3 sigma union x is bigger than mu plus 3 sigma, this is very small, and this is approximately 0.0026. So what you have is most likely you're going to be between mu minus 3 sigma and mu plus 3 sigma. So you could write it like this: mu minus 3 sigma, mu plus 3 sigma. So the probability x between these two, that is approximately 0.9974. Okay, so it's very unlikely you're gonna be 3 sigma away from mu on either direction, or more than 3 sigma away from mu in either direction. Okay, so, well, what do we need to do? First and foremost, we need to check that this is a proper density function. What do you need for a density function? One, you need that it's non-negative, which it clearly is. You take, if sigma is positive, and here you take sigma as the square root of sigma squared, positive square root, or if for that matter, if you write it as sigma square with the square root all the way till the end, you know, automatically you're talking about positive square roots. So clearly this function f of x, that's non-negative. So we do have that f of x, which I'm going to just write it like that now, 2 pi sigma squared e to the minus x minus mu squared over 2 sigma squared. This is for the whole real line. This is clearly bigger than 0. In fact, not just bigger than or equal to 0 for all x, but the requirement is bigger than or equal to 0. So we're going to just write bigger than or equal to 0. Okay, so yes, it does satisfy the first requirement for a probability density function. What is the second requirement for the probability density function? You need that the integral of the density over the whole real line is 1. So we need to check that this integral equals 1. And how do we do this? We have to integrate this crazy looking function from minus infinity to infinity. And what we'll need to do is actually call on some of the stuff we've learned in Calc 3. Okay, so let's start this integral, and maybe you along the way might also figure out how to do this. Okay, so let's write this down. Integral from minus infinity to infinity. Let's write down the constant outside. 1 over square root 2 pi sigma, or put the sigma square under the square root. It doesn't matter. E to the minus x minus mu squared over 2 sigma squared dx. Okay, so we need to do this integration. This is very complicated looking. So what we're going to do is first do a shift and a scaling to make this integral look nicer. So if you want, let's say y equal x minus mu over sigma. Okay? Then what do you get? Then dy equals 1 over sigma dx. All right? Okay? And as x goes to infinity, we've assumed that sigma is positive, y will go to infinity. And as x goes to negative infinity, y will go to negative infinity. Okay? So doing this change of variables, what do you have? This integral will change into, so this part, 1 over sigma dx turns into a dy. So you have 1 over square root 2 pi. That together turns into a dy. Limits, we saw that there'll also still be negative infinity to infinity. E to the x minus mu squared over sigma squared will be y squared. So you'll have minus y squared over 2. Now that's so much nicer looking than this integral. So we want to show that this integral is 1. So it suffices to show that that integral is 1. Okay? So we're going to show that. All right? So let's just evaluate. Integral minus infinity to infinity e to the minus y squared over 2 dy. Okay? And we want to show that this is equal to square root 2 pi because we want to show that this product up there times 1 over square root 2 pi is 1. Okay? So now, you know that over here, y is just a dummy variable in the integration. Okay? So what do you think this is going to be? Minus infinity to infinity e to the minus x squared over 2 dx. Well, this integral was going to be the exact same as this integral. Whatever letter you want to use. E to the minus infinity to infinity integral e to the minus t squared over 2 dt. That will be 1. No matter what letter you use over here, that integral you want to show that, sorry, it's not 1, that it is square root 2 pi. Okay, but no matter what letter you use over there, the integral is going to be the same. Okay, so let I be equal to integral minus infinity to infinity, e to the minus y squared over 2 dy, which we know is the same as e to the integral negative infinity to infinity, e to the minus x squared over 2 dx, or whatever letter you want to use. Okay, so we're going to do this. So we have that I squared. Let's just stick to these two. Will be the product of these. Okay, so minus infinity to infinity, e to the minus y squared over 2 dy times integral minus infinity to infinity, e to the minus x squared over 2 dx. Okay, all right. Now, let's evaluate this. Well, this is a number, correct? So we can take this number and put it inside this integral. So that's what we're going to do. Integral minus infinity to infinity, dx stays out, and this number we're going to put inside. Okay. And now we have this inside this integral. And as far as y goes, x is a constant, or any function of x is a constant. So we can take this and put it inside that integral. Oh, sorry. Yeah. So let's do that. Minus infinity to infinity. This was the x limits. And you have minus infinity to infinity. This were the y limits. E to the minus y squared over 2. This is a constant as far as y goes, so we can stick it inside this y integral because you can take constants in and out of integrals. Okay. This dx is a little far away. Okay. All right. So now we have an integral over the plane. All right. So let's put it all together. Minus infinity to infinity, negative infinity to infinity, e to the... What do you think you're going to do over here? You have e to the negative y squared over 2 times e to the negative x squared over 2. E to the a times e to the b is e to the a plus b. So let's add the exponents and you'll have minus x squared plus y squared over 2. Okay. So now this is an integral over the plane of e to the minus x squared plus y squared over 2. Now look at this a moment and think about how you would have done this integral had you got it in Calc 3. How would you evaluate this integral? You have an integral over the whole plane of minus x squared plus y squared over 2. There's no x's, there's no y's over here, so you cannot use substitution. This is a perfect example of when we need to convert to polar coordinates. Okay, so what do you remember? In polar coordinates, you have r squared is x squared plus y squared. Okay, dx dy or dy dx, it doesn't matter, is r dr d theta. And if x goes from minus infinity to infinity and y goes from minus infinity to infinity, then that means r goes from 0 to infinity and theta goes from 0 to 2 pi, right? So this is like you're going all through the plane. That means r goes from 0 to infinity and theta goes from 0 to 2 pi. So you're covering the whole plane. Okay, so let's make these substitutions. And what do you have? So theta goes from 0 to 2 pi d theta. And r goes from 0 to infinity. And this will be r d theta, right? Dx dy is r d theta. These are the limits. And this will be e to the minus x squared plus y squared is r squared over 2. Okay, well, take a look. What can you do now? In this situation, clearly you can do a u substitution. If you want, let u equals r squared over 2. Then du is... or minus, okay, let's just do minus, will be minus r dr, okay, and if r goes from 0 to infinity, what will you go from? R goes from 0 to infinity, you will go from 0 to negative infinity, correct? Okay. So let's write this. That will be integral 0 to 2 pi, integral 0 to minus infinity. All right, and this will be e to the u. R dr is minus of du d theta. Okay, so with this minus and the limits like this, we can switch it and make it negative infinity to 0, e to the u du d theta. You can do each of these integrals separately. 0 to 2 pi d theta, and integral minus infinity to 0 e to the u du. And what is this integral? This is going to be 2 pi. And what is this? This will be e to the u, and this integral will be 1. Okay. So that's nice. So we got that I squared is 2 pi. And that tells you that I is square root 2 pi, just as we wanted. I think this is a very pretty proof. It's very clever in that you made a change of variables and then introduced the same integral with x, looked at a product, and then changed the coordinates, and now you have that I squared is 2 pi and I is square root 2 pi. Okay, so when you go back to this, what do you have? That you found out that this integral over here is square root 2 pi. So you do have that 1 over square root 2 pi times the integral negative infinity to infinity e to the minus y squared over 2 dy is indeed 1. And that the integral of f of x dx from minus infinity to infinity is indeed 1. So yes, this is a probability density function. It is non-negative and it does integrate to 1. Okay, just using this very clever proof. Okay, all right, so we do have that it's a probability density function. Now what we're gonna look at is a little property about this random variable, which is normal with mean mu and variance sigma squared. So suppose x is normal with parameters so what do you mean? Actually, I got ahead of myself. I keep calling mu the mean and sigma squared the variance. I haven't proven that. That will come later. Okay, so let's just for now call them parameters. Suppose x is normal with parameters mu and sigma squared. Then what about the random variable y, which is ax plus b? Well, this turns out to also be is also normal and has parameters a mu plus a mu, so you have a times mu plus b, and variance, I'm sorry again, I shouldn't say variance, and a squared sigma squared. Okay, sorry, sometimes these tails of the sigmas come out very short. All right, okay, so we need to prove this. Okay, so how do we prove this? What we're gonna do is we're gonna look at the random variable y and figure out what its density is. And I'm gonna go through the proof of this because I think that the idea that we see in this proof is pretty nice and pretty useful in looking at functions of random variables. Okay? Okay, so let's try and find the PDF of y by first looking for the CDF of y. Okay, so let's look at the CDF of y. So f sub y of x. What is this? So every time we have more than one random variable floating around, make sure you put a subscript to know which random variables CDF or PDF or whatever you're looking for is. So f sub y of x, that is the probability that y is less than or equal to x. All right, but what is y? That's the probability that ax plus b is less than or equal to little x. What is that? That's the probability that x is less than or equal to x minus b, bring the b over and divide by a, x minus b over a. What is this though? This now is the CDF of x evaluated at x minus b over a. Don't you agree? Right? This is exactly the probability x less than or equal to alpha equals f sub x of alpha. So you have alpha equals x minus b over a. All right. So this is the CDF of y. Well, we're not going to. You should not try and integrate the density of x from negative infinity to x minus b over a. You cannot integrate this function, and that's why we had to do that whole I squared trick. That function does not have an antiderivative that you can write down. Okay? So we right now just have a relation between the CDF of y and the CDF of x. Okay, so what do we do now? We want the PDF of y. So can you think of something you can do to this equation to get our hands on the PDF of y? You do know the PDF of x, right? Because x is normal with parameters mu and sigma squared. And that's how we started this section. We looked at what the function was. That's the PDF of x. You remember 1 over square root 2 pi sigma e to the minus x minus mu whole squared over sigma squared. That was the PDF of x. So we do know the PDF of x. We want the PDF of y. Here's a relation between the CDF of the two. So how can we go from the CDF to the PDF? You want to differentiate. Okay, so that's what you do now. Go ahead, differentiate both sides with respect to x. RT stands for with respect to, and you have differentiate with respect to x. Okay, and what does this become? This will be the PDF of y. And how about this? Now we have to use the chain rule. Okay, sorry, I should use a curly x. Over here we'll use the chain rule. So what do you have? You have 1 over a, that's the derivative of the inside with respect to x, times the derivative of the outside with respect to x, which is the CDF differentiated gives you the PDF evaluated at the inside. Okay, or if you wanted, I could say that, here, let me write this. Okay, so this is the derivative of capital F evaluated at x minus b over a. Okay, so that's what I mean. Anyway, let's go back to writing what we had. Okay, so there we go. We have the PDF of y now. So what we need to do is take the PDF of x, evaluate it at x minus b over a, and multiply it by 1 over a. Okay, we'll do that. So 1 over a. This is 1 over square root 2 pi sigma e to the minus. So normally you know f sub x of t is 1 over square root 2 pi sigma e to the minus t squared, t minus mu whole squared over 2 sigma squared, right? That's what this is. So we'll plug in place of t, I have to put x minus b over a in this equation. Okay, so let's do that. Okay, so a little bit of algebra will show you. You have this, and taking a common denominator, in the numerator up here you have x minus b minus mu over a whole squared divided by 2 sigma squared, which is exactly 1 over square root 2 pi. I'm just going to write it my way, a sigma squared, e to the minus x minus b plus a mu, sorry, there should be an a mu, over 2a squared sigma squared. Now take a look at this. What is this? This is exactly the density of a normal random variable with what mean? It has the mean given in that bracket. So a mu plus b and variance, or actually, sorry, once again, I'm jumping to mean and variance, I should say parameters. A mu plus b and a squared sigma squared. Okay, and these do turn out to be, that does turn out to be the mean, and this does turn out to be the variance. All right. Okay, so we've seen that if you have a random variable with parameters mu and sigma squared, if you scale and shift it, you also have a new random variable, and the parameters do get scaled and shifted according to this formula. All right? Okay. And now let's take a random variable with parameters mu and sigma squared and find out what their mean and variances are. Okay, so therefore this whole thing that I keep doing, calling this mean and calling this variance, that'll be okay then. Okay, so let's take a look at that. So suppose that x is normal with parameters mu and sigma squared. All right, let's find out what the mean and variances are. All right. Okay, so let's do that. So what we're going to do is first let z be equal to x minus mu all over sigma. Okay, so we've shifted and scaled it. All right, so we've created this new random variable. And what do we have? So I can write this as 1 over sigma x minus mu over sigma. Okay, and we want to find out what the expectation of z is. Okay, what will be the expectation of z? This will be the integral from minus infinity to infinity, z times the density of z. Okay, you do know the density of x. All right, and using this shift that we just learned about, what will the density of z be? The density of z, and that's, you can do this little exercise. The density of z will turn out to be e to the minus z squared over 2 times 1 over square root 2 pi on the whole real line. So that's what this turns out to be. Okay, and so now you have this. You could do this, actually work this integral out by actually doing a u substitution, or you can observe what kind of function you have over here. Okay, you have an odd function that you're integrating from minus infinity to infinity, and so the integral is 0. Or actually go ahead and do the u substitution and do the integration, and you have that this integral turns out to be 0. Okay, and how about the variance of z? That is the expectation of z squared minus the expectation of z whole squared, but that's 0, so that's the expectation of z squared. Okay, what will this be? Same thing, just like before. Then this turns out to be integral minus infinity to infinity z squared e to the minus z squared over 2 dz. What you'll have to do is do a little integration by parts, okay? And this you will see will turn out to be 1. Okay. How would you do this integration by parts? You can split this up. Z times z e to the minus z squared over 2. Okay. And let u be z and v prime be z e to the minus z squared over 2. U prime will be 1. V will be e to the minus z squared over 2 with a minus sign, and do the integration. It'll be u times v minus integral u prime times v, and you use the fact that the integral of the density is 1, and you will get that this equals 1. Okay, so we have that the expectation of z is 0 and the variance of z is 1. Okay, however, you have that z equals x minus mu over sigma. So x will be sigma z plus mu. All right, so expectation of x will be expectation of sigma z plus mu. So that is sigma times the expectation of z plus mu, and this is 0, so this is just mu. And the variance of x is the variance of sigma z plus mu. Okay, and you know that will be shifting a random variable doesn't change its variance, so that's not going to do anything. The sigma will come out as a sigma squared, and you have sigma squared variance of z, which is 1. So you have that this is just sigma squared. So I've always been calling the parameters mean and variance, and this shows you that when you have a normal random variable, the first parameter that you conventionally call the first parameter is the mean, and the second parameter is the variance. Okay? So, go back for a second to the density of a normal random variable, or for that matter, the density of a normal 0, 1 random variable. Either one, it's fine. Okay, so the density of a normal 0, 1 random variable is this. We saw e to the minus y squared over 2 times square root of 1 over 2 pi, or 1 over square root of 2 pi, or this over here in 1 is the density of a normal random variable with mean mu and variance sigma squared. Now take a look at this. If you wanted to calculate probabilities with this function, what do you have to do? Normally, what you have to do is take the density function and integrate over intervals. Well, this function does not have an antiderivative in a closed form. So you cannot integrate this function. You'll have to do numeric integration or some kind of Simpson's rule or something like that. Okay? So what one does is you do not integrate it. In fact, what you do is, one, you use the property that if you shift and scale a normal random variable, then you will have a normal random variable with mean 0, 1. So if x is, if you take x minus mu over sigma, then that random variable will have mean 0 and variance 1. Okay? And what you look at are, you look at probabilities associated with the normal 0, 1 random variables, and those are given in a table. They've been calculated using numeric integration, and they've been calculated up to 4 decimal places. You use those values in order to find probabilities associated with a general normal random variable. Okay? So here's what I mean. Like, for example, suppose you're looking for probability x less than or equal to, um, suppose you're looking for probability x less than or equal to r, okay? Then what do? You look at probability x minus mu will be less than or equal to r minus mu. And that will be probability x minus mu over sigma less than or equal to r minus mu over sigma. But what do you know? This random variable is actually the normal 0, 1 random variable as we just saw above. Okay? So this probability is the same as this probability. How do you find this probability? Those probability values have been given to you in a table, which are the normal 0, 1 tables in your book. And of course, in any test or anything, you'll be given these tables. And you will look up the value under r minus mu over sigma. Okay? So that's what we need to do. So let's apply this, do some examples with this first. Okay? All right. Okay, so here we go. Example, x is a normal random variable with parameters four, mu equals 4, and sigma squared equals 25. All right. And what we want is, let's find the probability that x is between 3 and 5. Okay. Let's find the probability that x is bigger than 6, for example. And C, let's find the probability that x minus 4 is bigger than 1. Okay? All right, let's do this. Okay. So what do we have? Let's take a look. Probability x is between 3 and 5. How do we calculate this? Like we said, what we need to do is subtract the mean and divide by the square root of the variance, which is the standard deviation. And if you have an inequality, if you do it to one of them, you have to do it to all three of them. So let's just subtract the mean first. Okay. So, and then let's divide by the sigma, which is square root of 25. And this is what we get. Okay, so that's the probability of -1 over 5 less than, and what does this turn out to be? That's just the normal 0, 1. Less than 1 over 5. So this is what we have. Okay, now in the tables, what we have is phi of t. What is phi of t? In the tables in the book, you're given phi of t, and this is just the CDF. That's the probability that z is less than or equal to t. And in the tables, we only given, in the book, we're just given for these values for t bigger than or equal to 0. Okay, so let's just see. You have 0 over here. This is 1/5, and this is -1/5. What we want is this area. Well, how would you calculate that area? What you have over there, you could do it in multiple different ways. I'm just going to do it in this one way. The table will give you phi of 1 over 5. Okay, that's the probability that z is less than or equal to 1 over 5. That's what the table gives you. All right, and that turns out to be 0.5793. If you look under the table in 0.2, this gives you 0.5793. So what is this area? This whole area is 0.5793. Okay, so now that you know this, do you know what this dotted region is? What's the dotted region? What is the area over here? This area will be 1 minus 0.5793, right? So that is 0.4207. That is the probability that z bigger than 1 over 5. Okay, and in fact, that's going to be the same as the area to the left of negative 1 over 5. So this is the same as the probability z less than negative 1 over 5. Okay, so what's the probability that z is between negative 1 over 5 and 1 over 5? Well, it'll be 1 minus 2 times 0.4207, or 1 minus 0.8414, or that is the same as 0.1586. Okay, so that's the probability that z is between negative 1/5 and 1/5, which is exactly the probability that x is between 3 and 5. All right. Okay, so that's your answer to part A. All right. Question, part B. You're asked, what's the probability x is bigger than 6? Well, let's figure this out. What do? Same thing again. Probability x minus the mean, which is 4, divide by the standard deviation, which is 5, bigger than 6 minus 4 over 5. So that's the probability, and this is z bigger than 2/5. What is 2/5? 0.4. Okay, how do you find the probability that z is bigger than 0.4? How do you find this? That is 1 minus the probability that z is less than 0.4, which is what you have in the tables. Okay, and that is 6554. And that is 0.3446. Okay? And lastly, part C, what you're asked is, what's the probability that x minus 4 in absolute value is bigger than 1? Okay. Well, what is this? This is, you want x to be at least 1 away from 4. This is the same as the probability that x is less than 3 union x is bigger than 5. Correct? And that is 1 minus the probability that x is between 3 and 5, which is what we've calculated in part A. And we already know that that is 0. This is 0.8414. All right, so with absolute values, convert it to the regular interval notation. And it's easy when you are subtracting the mean, then you know it's symmetric, and write down what those probabilities are. All right, so this is how you deal with the general normal random variable with non-zero mean and a non-zero variance. Okay? All right, So you should look at the questions in the book. There's four other examples in this, three other examples you should look at in this section. Many examples at the end in the homework also dealing with normal random variables, okay? What we're gonna look at next is, actually, sorry, before this, what we're gonna look at, what I do wanna mention, I'm not gonna do an example in this, is suppose I tell you stuff like x is some normal random variable, okay, with some unknown mu, all right, and I tell you that the variance is 16. For example, suppose I tell you that. And suppose I tell you that probability of x being bigger than 12 is equal to 0.1151. Suppose I tell you something like this, okay? Then I tell you find the mean mu. What do? You translate this to a question about z and actually look up the tables in reverse, okay? I'm just gonna do this. So you have probability of x minus the unknown mu is bigger than 12 minus the unknown mu over the sigma, which is 4. And this you know is 0.1151, right? I just took this and subtracted mu from both sides and divided by 4 to both sides, and you know this is 0.1151. Well, what is this? You know this is z, so probability of z being bigger than 12 minus mu over 4 is 0.1151. Okay, what does that tell you? That tells you that the probability of z less than or equal to 12 minus mu over 4 is 1 minus this is 0.8849. Okay, so can we find mu using this? Well, if we look at the table, so go to the table, and what you want to do is look for where you have values closest to 0.8849. Don't look up as your x equals 0.8849. You want, this is the area, okay? So you want to find a value t such that this is 0.8849. So if you look in the table, you have to look at the table part, not at the x column, the first vertical or top horizontal column. You look in the tabular part and you see 8849 comes up under 1.20. So you know that phi of 1.20 is 0.8849. Okay, so what is this? That tells you this is phi of 12 minus mu over 4. So you know that 12 minus mu over 4 should equal 1.2. And using that, you can find the mu. 12 minus mu is 4.8, or 12 minus 4.8 is your mu. Okay. And that tells you that 7.2 is mu. Okay. You could also have another example where you don't know the mu, you don't know the variance, so you don't know two pieces of information. So I will give you two pieces of information. So something like this along with another one, and then you'll have two equations and two unknowns, and you find the mu and the sigma squared. All right. Okay, so that takes care of examples for normal random variables with variance sigma squared and mean mu. Let's move on to approximations now. Okay, so you remember in chapter 4 what you looked at are approximations to binomial random variables. All right, what did you do in chapter 4? You looked at a Poisson approximation to binomial in chapter 4. When did you do that? When your p was very small. So for very rare events, you could use Poisson approximation to binomial. Okay, now it's very easy to look up normal random variable tables, and in fact, when n is very large, to calculate binomial values, that can get very tedious. All right, so what do we have? We have that, in fact, if n is large, so n is very large, then the binomial random variable, if you look at the bar graph or the histogram, it looks a lot like a normal random variable curve. All right? And that's just kind of a small lead to the fact that you can use normal approximation to binomial when n is very large. All right? And in particular, you can say that normal approximates binomial when n is large. And, when that really depends on how good of an approximation you want. But in general, we say the approximation is good when n times p times 1 minus p is at least 10. All right? So when you have n times p times q, or n times p times 1 minus p bigger than or equal to 10, then you can use a normal approximation to binomial. All right? I'm just going to show you a little histogram, or the bar graph. So if you remember, if you look at the probabilities for a binomial random variable, they kind of look like this. They don't have to be exactly symmetric. Something like this. It does kind of look like a normal random variable curve. Okay? And so, what do you have? Suppose you have any value, all right? Some number k. All right? And you draw your histogram or bar graph like this. And what is this? That'll be k plus a half. And that end is k minus a half. Okay, and suppose I want, what is the probability that this x, let's say, is binomial NP? What's the probability x is less than or equal to k? I'm asking you that. Then what do you want to do? In reality, what you do is you add up all the bars, areas, probability x equals k minus 1, x equals k minus 2, and so on. You will sum up all these probabilities. All the way down to 0. Okay, and you might be wondering, like the normal random variable, the graph is infinite, but the binomial random variable, there's nothing, the probability x equal any number less than 0, of course, is 0, and equal any number bigger than n is 0. But, when n is large, these areas, if you draw a normal curve on top of this binomial curve, the areas to the left of where x equals 0 and where x equals n, the area under the curve is very, very small. So it's fine. You can say normal is a very good approximation to binomial when n is large. Okay, so normally this is what you want to do. And in a bar graph, what is this probability? That probability is exactly this bar has width 1 and height equals to the probability. So you can say each one of these probabilities is the areas of each one of those rectangles, correct? So that's the area of the rectangle that's over here. And what is this? This is the area of this rectangle, all right? Going from here to here in that double zigzag and so on. Well, take a look at this. We can say, if you look at, instead of the bar, you will see that approximately just excuse my drawing now. Go to k plus 2. All right, here was your graph for, here was the bar for k. Okay, instead of adding up the areas of all these bars, I can just look at the area under the normal curve to the left of k plus a half, right? Okay, so you can say that the probability that x is less than or equal to k is approximately equal to the probability that this normal curve, which I'll tell you what it is, less than or equal to k plus a half. Okay. What do I mean by this normal random variable? I just mean the normal random variable that has that PDF. All right. Okay. So I'm going to make this more concrete now. Okay. Suppose x is binomial with parameters n and p. So n trials, p is the probability of success. Okay? Then you have that x is approximately normal with mean equals what? What do you think the mean of this approximated random variable should be? Well, at least you would want the mean of this approximation to equal the mean of what x was. You remember what the mean of a binomial random variable is? NP. Right. And variance equals the same as the variance of x. You remember what the variance was? NP times 1 minus p. Okay. So that's what you have. So suppose x is binomial NP, then it's approximately normal with mean equals NP and variance equals NP times 1 minus p. And these are not a surprise because that's exactly the mean of a binomial random variable, and that's exactly the variance of that binomial random variable. Okay? So let's take a look at an example to completely understand what's going on over here. All right? Okay. So let's say x is the number of times that a fair coin, this is example 4G in the book, okay? X is the number of times a fair coin that is flipped 40 times lands on heads. All right, so it's the number of times, you're counting the number of heads. A fair coin, you flip it 40 times, you're counting the number of heads. Find the probability that x equals 20. Use a normal approximation and then compare it with the exact solution. Okay, so x is number of heads when fair coin is flipped 40 times. Okay, we're asked what's the probability x equals 20. All right, so we want the area of this, the real value is exactly the area of this bar in the bar graph for a normal random variable. Okay, so the true value is 40, choose 20, p, that's the p, it's a fair coin, raised to 20, 1 minus p raised to 40 minus 20. So that is 40, choose 20. 1 over 20 raised to 20 times 1 over 20 raised to 20. So that's 1 over 20 raised to 40. All right. And this turns out to be approximately, actually we should use squigglies, 0.1254. Okay, so when you punch these into your calculator, 40 choose 20, 1 over 20 raised to 40, you'll get approximately 0.1254. Now let's use normal approximations. Okay, so probability x equals 20. All right. Okay, what do we say? Well, we want the area of this. Okay, and you have the uh, background normal curve. Um, let's also actually just make sure that the approximation is okay. NPQ should be bigger than or equal to 10. What's N? 40. What's P? 1/2. What's Q? 1/2. So that's 10. That is bigger than or equal to 10. So the approximation is okay. Anyway, in the question, they ask you to do the approximation. So probability X equals 20. What do? We're going to use normal approximation. Now, you would just say, oh, fine. If I approximate by a continuous curve, then the probability that continuous curve equals any value is 0. So the answer is 0. So it's terrible approximation. But remember this. Remember, we needed to do the shift to the right to include the whole curve, the whole bar for X equals K. So if we want the area of this bar, which is the probability exactly equal to the probability X equals 20, we should go a little to the left and a little to the right to include the whole bar. Not a little, meaning half to the left and half to the right. So this is the same as X being between 20 minus a half and 20 plus a half. Okay, so that's the probability 19.5 less than X less than 20.5. All right, and now what do you want to do? You go throughout and subtract the mean of X. It's 40 times a half, that's 20. And what is sigma, or sorry, variance of X is NPQ, that is 10. So what we need to divide by is square root of 10. And what we have is 19.5 minus 20 less than X minus 20 less than 20.5 minus 20. Divide throughout by square root 10. And this you know is Z. And these are approximately negative 0.16 and 0.16. So this is the probability you want to calculate, so you can just look up in the tables. And, you know, we don't have negative values, but I showed you earlier how to figure that out. And what you have is this is 0.1272. Okay? And you can see it's a pretty good approximation to the actual value, even when you're just looking at n equals a certain value. All right? So this showed you that when you want to approximate, make sure you don't forget to shift to the left or the right by drawing a picture and asking yourself, what area am I looking for? Okay? Let's do one more example to make sure that this makes sense. Okay, and I'm gonna just do the example from the book. And that's example 4H. Okay, the ideal size of a first-year class at a particular college is 150 students. The college, knowing from past experience that on average only 30% of those accepted for admission will actually attend, uses a policy of approving the application of 450 students. So they're gonna admit 450 students, and in their mind, from historically, they've seen only 30% attend, so they're assuming about 30% of those 450 will attend, and the capacity is 150. All right, so compute the probability that more than 150 first-year students attend this college. All right, so what do you have? You want to know how many people will actually attend. So let X be the number of students that attend. Okay, they have admitted 450. And historically, they know that the probability a student attends is 0.3. All right, so you know that X is binomial with N equals 450 and P equals 0.3. All right. The question is, find the probability that X is bigger than 150. That is, more people attend than the capacity. Okay, that's the question. All right, so let's take a look. Firstly, I like to draw this. So let's say that's the bar for 150. Okay, here's the bar for 151. You want the probability X is bigger than 150, or you could think of this as probability X is bigger than or equal to 151. Okay, so what do you want? You have this. You want the area to the right of this line, right? To the right of this line. So you want the probability that X is bigger than or equal to 150.5. All right, don't forget to make this correction when you're doing a continuous approximation to this discrete case. Okay, and then that way you'll be looking at all the appropriate bars. Okay, and now what do? Now we'll do normal approximation because NPQ you can check is bigger than 10. So you can do normal approximation. Okay, so what do we need? We do need what the mean of X is. Mu will be the mean, and that will be 450 times 0.3. Okay, and what will be the variance? That will be 450 times 0.3 times 0.7. All right, so you will look at probability of X minus 450 times 0.3 over square root of 450 times 0.3 times 0.7, bigger than or equal to 150.5 minus 450 times 0.3, divided by 450 times 0.3 times 0.7 under the square root. Okay, and this is approximately probability Z bigger than or equal to this value, and that turns out to be approximately 1.59. Okay, this is approximately 1.59. Actually, let's do squiggles because it's approximate. And what do? How do you find the probability that a normal random variable is bigger than 1.59? That will be 1 minus what the table says under 1.59. Okay. And that is approximately 0.0559. Okay. So there's approximately a 5% chance that by admitting 450 people, they will have more students who attend than the number of seats. So, and in fact, what the question could also be asked to you in this way: how many people should they admit? So find N. How many people should they admit? So what you have over here is this won't be 450. It'll just be some value N. So that the chance that they are overloaded is less than 2%. Okay? So think about that problem. What do? Over here, everywhere I've underlined, you will have an N. And over here, you will want to have 0.02. Okay, find out what that is. Phi of 1 minus phi of what? Work backwards. And you will solve an equation with N. All right? So that's an interesting problem you can try. I'll write this down. What should N be? And of course, there'll be a lower bound. An upper bound. What should N be such that the probability of overloading is at most 0.02. Okay, so if you want, I can write what is the maximum n can be such that the probability of overloading is at most 0.02. So try this and you will have x is binomial n and p equals 0.3. Okay, and you want to find probability x bigger than 150. You want this to be equal to 0.2, or really less than or equal to 0.2, and then you find what your n should be. You'll have to solve a quadratic in that. Okay, so I hope this section's clear and all the properties of normal random variables, normal 0, 1 random variables. How do you take a normal random variable and approximate it by binomial? I hope all of those aspects of this section are clear to you. And as usual, email if you have any questions. Okay, and the next next video lecture, we will do section 5.5. All right, take care.